Hi everyone, I'm Andrea. I have been a Scala programmer by trade for a while, and I'm now jumped to academia. I'm a PhD candidate at ETH Zurich. And what I figured out while doing my master thesis last year and learning Rust is that there's some interesting things we can learn from other languages to make programming in Scala, and especially type classes, a more pleasant experience. And I'm going to go through that in this talk. So let's start with a brief summary of what we're going to cover. The first thing is, if you're not familiar, I've seen not all the hands going up when they've asked. I'm going to introduce what a type class is from the perspective of the type system and from the perspective of what Haskell or how Haskell does it. Then I'm going to look at what they look like in Haskell, where they're a first-class citizen of the language. And I'm going to look at what complications arise from the fact that we are encoding them in Scala using other features of the language. And then we're going to go through a few case studies from other languages and other libraries, and libraries in Scala, to see if we can figure out a few good practices for the use of type classes in Scala. So what are type classes? They're a way to attach functions to existing data types. Or in other words, support ad hoc polymorphism. What does it mean? So let's look at this small example. We have 3 case classes. They're shapes. We want to, for example, compute their area. And we have 3 functions, one for each type. And then we would like to write a function that takes 2 of these shapes and computes and compares the area of the 2, or actually just takes the difference. And we would like to say that the things that we pass to these functions can have to be types that support the operation area. So we can actually call area for those types and get an area out of it. So if you do this right, we would like to see something like compare area with 2 shapes working correctly. And obviously that's not valid Scala code, it's just to prove the point. And so what we can do, of course, if you're familiar with subtyping, is to just define a trait that defines our area function, have our 2 case classes extend that trait, and implement the area function, and do the reasonable thing here. And then we can obviously have the function that we're interested in, take 2 parameters of type hasArea, call area on them, and be done. But maybe there's another way. We can group types for which certain operations are supported without having to define those operations in a trait that gets extended. And so we can retain the ability of defining those operations separately from the types themselves. So in this case, we want to be able to take these 3 functions defined ad hoc for these types and not in any of their supertypes, and be able to use them in a meaningful way. So here's a more not compiling Scala code. Let's assume we could be able to write this. We could be able to say, hey, there's a type class hasArea that says that for some type t, we have to be able to compute their area. And once we have this, we can say, all right, we can write a function that takes 2 parameters that in some way support the operation that we'd like. And here, we'll see that type variables A and B will only be able to be instantiated to a type whose members support the operations associated with the type class hasArea. So we need to do 2 things for this to work. First, we need to define which operations we'd like to support. And then 2, we'd like to add the types to the group that supports those operations. So we'd like to say that square and circle belong to the group of types that support area. So how do we do this? First, define the supported operations for a type class. In Haskell, it looks something like this. We say class, and here class is a keyword of the language, is valid Haskell code, and it defines a type class. The type class has name hasArea, takes a type parameter A, which is the type for which we can support the operation. And then we say that the operation is something like taking an A and returning a float. This is what it might look like in Scala if type classes were, in fact, a first-class citizen, but they are not. Two, we need to add some types to this family of types that support this operation. And so in Haskell, we would define the equivalent of the three case classes. If you're not familiar with Haskell syntax, it's not a big deal. Those are essentially equivalent to what we saw before. And we define, again, the type class we wanted. And then we need to add these types. And the way we do this is by defining type class instances. And don't be confused, these are not instances of a class. They're not objects. They're just an overloading of the concept of instances in this case. And we are saying that we know how to compute area for these three types, square, rectangle, and circle, using those operations. And that's how you define the function in Haskell. So once we have that, we can use this hasArea type class to restrict the parameters of a function, so we're actually able to call those operations on the parameters. So in this case, for example, we have a hasArea again, and so let's just parse this function syntax here. We have a function that takes two values, x and y, and their type parameters are a and b right at the end there. And the two constraints we define with the big fat arrow is that both a and b must support the area operation, and they could be different types because they are two separate type parameters. So here's a complete example of how this might look like in Haskell. We have the three classes, then we have the type class, the instances, and a function that makes use of these operations that we defined. Now, we've seen how this is in Haskell. This is pretty straightforward. It's a main piece of it's a main feature in Haskell, and it's used throughout the language. In Scala, things are a little different. We can support type classes, but they are not a first-class citizen. And first of all, to introduce how we can use them in Scala, we need to take a look at implicits. So implicits are a feature of Scala you may be familiar with. Who's familiar used implicit here in this room? Can you shoot up your hand? All right, it's almost everyone. That's great. So just to be extremely brief about it, we can ask the compiler to find as a value for a parameter of a function without having to pass it explicitly, and it's only going to be found if there's an implicit value in scope of the corresponding type. So again, how we define a type class in Scala and how we define the instances, the type that belong to that group. Here we go. Type class definition. It looked like that in Haskell. In Scala, we just define a trait. But note the difference. Before, when we were doing subtyping, there was no type parameter here because we would end up extending this trait. But here, in this case, we are encoding the fact that our operations apply to a type A into the type parameter A of the trait. And again, we have a function A that takes area that takes any parameter and returns a float. So then again, we want to be able to define instances for this type class, which means which operations are supported. In Haskell, we have already looked at how that's done. Let's look at Scala. The case class is as always, but the difference here is how we provide an implementation. We're going to say that we have an hasArea of square, and here hasArea is the trait we defined before. And the definition is this one, is an instance of that trait declared, so actually an object declared right in line. There are various different ways to do this, but this is a fairly good example. And here we are saying that we will have in implicit scope a hasArea of square for with this implementation. So let's look at how we can use then the type constraint we've defined. So we have this type class. We may want to use the operations defined in there with other functions. And so what we can say is that a function compareArea requires, again, A and B to implement hasArea so that we can call area on them. And there are two syntaxes here. They are equivalent because the second one the sugars to exactly the same equivalent form, which is the first one. And what we're saying is that every time we take an A and B, we also want to have the implementation of has area for both A and B. So let's move on to how to make it nice to call those operations on the types. So in Haskell, if we want to compute the area of a type of an instance of a type that supports our operation, it's just as easy as to call area on the value. But in Scala, this is not the case directly. We can't just say square.area because that function is not defined on the class itself, on the trait, or any of its supertypes. We have to do something more. And what we do here is we say that we have an implicit conversion from any type that supports the operations in a has area to this new implicit class that directly supports the operation area. And so once we have these in scope as well, we are able to call area on it. So there's a bit of boilerplate, as you can see. Here's a complete example. We have the trait definition, one implementation for square. Obviously, we can have more, one per type that we want to support. And then we have the so-called object-oriented forwarder or syntax, so we can actually call area on the type. And in the end, once we have all of this, we can write something like the line at the bottom. And you can see I'm writing a lot of Rust because I put brackets after area on the last line. And so what we can now take a look at is, okay, we have figured out what type classes are, how they're encoded in Scala. Can we take a look at other languages that support them natively and learn something from them for their usage, for how to make the code less verbose? First of all, in Scala, the type classes are encoded as implicits. And so finding an instance of a type class, so an implementation, is the same as finding the corresponding implicit. And so let's look at instance scope, where this search for implementation is done. First of all, definition, Orphan instances. An Orphan instance is any type class instance that's defined neither in the same module as the class or the type, nor in the same module as the type class itself. So if you have a file or module that defines the type class, somewhere the trait, and you have a module somewhere else that defines your square or circle, if you don't define the instance for square or circles in any of those files but somewhere else, that would be an Orphan instance. So in Haskell, the idea is pretty simple. There's no implicit resolution system, and that's the so-called open word assumption. So an instance of a type class that you define anywhere will be passed down to all the modules that inherited, and it flows through those imports. So if you have a chain of imports that at some point end up importing some module at the top, you would see any type class instance you've defined there. So let's say you have module A, B, and C. B imports A, and C imports B. You will see anything that was defined in A in module C as well. So, and also importantly, this is true for any type class instance, regardless of whether the type class itself, the name of the type class, has area in this case, is in fact imported in your module. Rust. Rust, if you're not familiar, is a systems programming language from Mozilla. They've been using it to write a new implementation for the Firefox renderer. It's a very cool language. I know there's a conference about Scala, but I've been very happy with it. And instances in Rust can only be defined in the same file as the data type or the type class. And here I should point out, type classes are essentially a first-class feature in Rust as well. They are not called type classes in Rust, but they essentially are. And so we cannot have Orphan instances. And instances are always available once we have imported the trait that represents the type class. Scala. Scala is a little bit more complicated because we have the implicit resolution. So, two rules. The most specific implementation that could be found is the one that will be used. Second, the search for instances is done in the implicit scope and in companion objects. Let's unpack that. Most specific first. We have some type class of T, and it supports an operation where it just returns a string. We have two implementations. One is for any T, so we can define implementations for a family of types, in this case for all types. And we're saying that for any T, there's an implementation of some type class where the operation returns generic. Otherwise, we also have an implementation specific for string. If we were to have both in scope at the same time, once we ask for an instance of this type class for string, we would get the most specific one, the one just for string, because that's more specific than any type that we can have. Then, once we have figured that out, we also need to look at what happens if we have instances in multiple origins for the implicit resolution in Scala. And so, first of all, the Scala compiler will look in implicit scope, which is the local scope, so anything it's been defined in the current or parent block. Anything that was imported or inherited explicitly. And importantly, if one instance is available both in the local scope and has been imported or inherited, we would end up with an ambiguous implicit saying, okay, you have two instances, I don't know which one to pick. If nothing is available there, also importantly, among imported and inherited values and definitions, the one defined for the most specific type is the one that's going to be picked. The rule we saw in the slide before. Also, the companion object of the data type or the type class is a good place to put a type class instance because that's the fallback. If there was nothing found in the local scope or imported or inherited values or definitions, then we're going to look in the companion objects of hasArea and of square, rectangle, and circle, depending on which one we're using. So here are a few issues that I've encountered while using type classes in Scala. They're not deal breakers in any way. Type classes are absolutely great, but it would be good if you could do something about this. First, readability. Because we have so many places Scala could look for an instance of a type class, when we see its usage, we don't necessarily know where it's coming from. Second, discoverability. Same reason, but how do we know which instances are available in our code, in our libraries for our type, if we don't know exactly where to look? And finally, coherence and maintainability. So, because you can have multiple instances, how can we tell which one is being used and what happens when we move code around? And we're going to go look at those in depth in a second. So first of all, coherence and maintainability. Let's say that we have hasArea, we have an implementation for rectangle defined in the companion object. And also, we are going to define another instance inside our module where we're writing our code. So think of this as being a piece of library on top or another compilation unit. And then this is your code of your web request handler, for example. And what we see here is that we have another definition of how to compute the area of a rectangle. So if you know something about geometry, if you are computing the area of a rectangle on a plane or on a sphere, those areas might be different. If you don't know what I'm talking about, trust me, they're different. They're two different contexts. So we're saying that the way we compute the spherical area is different. And I'm going to even provide implementation. It doesn't matter. And so once we call compare area here, because of the rules we saw before, we are going to pick the innermost implementation, which is the one directly in scope. And so we are going to compute the area for the two rectangles on a sphere. But what if we were to take that line of code and move it somewhere else in the project, somewhere we haven't not defined this other implicit? Then the behavior of this function call would change. We would end up using the implementation defined in a companion object. One more problem with coherence. If we have blanket implementations, so here's an example. We have a codec to encode a certain type to JSON, and then we have a codec to encode a certain type to a value that we can store in a database. And in this case, both are type classes, obviously, and we're saying if we know how to encode something as JSON, then we know how to encode it to the database. We're going to assume that we're just going to encode it in JSON before giving it to the database. And here it should be TNT, obviously. Then what happens if instead of having just a JSON encoding, we also have a binary encoding for the same type? And we are saying, okay, for both, it makes sense to use that encoding to store the piece of data in a database. So we define two ways of doing that. And now, when we end up trying to use that, and we provide both implementation for square of both codecs, how do we know which one Scala is going to pick? That's going to depend on what's in scope. So here are a few things we can learn from Haskell and Rust for Scala typeclasses. First of all, it's a good idea to define instances in companion objects if you don't have any other restriction. And the reason for this is that it's easier to find them. You just can look up the companion object of your type or type class, and you're going to find it. And it's clear which one you're going to end up using. Then, if you have to define blanket instances, so instances across a lot of types, again, good idea of defining them in the companion objects of the target type class. So in this case, how to encode to the database, the DB codec we saw before. And this makes it, again, easier to find those implementations. One more. It's good to be conservative and follow a convention for orphan and blanket instances. But we're going to go into details later with another case study. So we saw before that we need to do some ceremony to be able to call area directly on a certain object that supports a certain operation in Scala. If you don't do that ceremony that we talked about before, you end up having to say implicitly, get the instance of the type class, and then call area and pass it the parameter you wanted, which is not ideal. And in comparison, in Haskell and Rust, you end up having those functions defined and imported along with the type class definition. In Scala, otherwise, however, we end up having to do this. We have our implicit class. We saw this before already, which forwards our call to area to the right type class. So let's take a look at how Simulacrum simplifies a lot of this. So Simulacrum is a great library that uses macros to simplify how you would end up writing type classes in Scala. It requires microparadise, and the way you use it, it's something like this. You just import Simulacrum, and any trait that you know is going to be a type class, you just annotate with @typeclass, and it's going to do a few things for you. First, it's going to define that trait, that type class we wanted. Second, we now know that we need those object-oriented forwarders, those things to call area directly on objects. Simulacrum is going to generate that code for you, and it's going to generate a trait ops A that ends up doing the right thing for forwarding the object. The details here are not important. And it's going to do it in a way that lets you have that trait, that provides that implementation separately for managing your imports by using the cake pattern, for example. But you also get, by default, the operations in the object, companion object, under another object called ops operations. So once we have that, we can use the syntax directly. But what if you didn't want to use Simulacrum, but wanted to do something similar? We could do something like that. In the companion object of the trait as area, we define an object operations, that's are the operations that we support, and just define that implicit conversion we saw before. So once we have this, obviously the result is we can import has area ops underscore, for example, and we are able now to call area directly on the object. Additionally, if we are using Simulacrum, then we have this object. So we have these traits we can mix in as we want. Geometry ops here supports area, for example. As area ops supports area, for example. And we can mix in a bunch of these in a single import that we can then use directly. And this is to avoid having to import operations for all the type classes you're using. More importantly, Simulacrum does not override the type class companion object when it does its magic. And so we are still able to provide implementation for type class instances in the companion object itself. So this is totally fine. We're providing the implementation for rectangle in the companion object of as area, and that will not be overwritten by Simulacrum. Why Simulacrum? It's robust, and it provides a consistent and object-oriented forwards. You find them in ops. The add type class marker is easy to search in a code base, so that helps with discoverability. And if you wanted to be a little more advanced and cut down a little bit on the imports, we can use syntax via traits. We can mix in syntax via traits. So what we learned from Simulacrum, for discoverability, we define the syntax in the companion object, and we export it via operations and traits for usability. Cats. Cats is a well-known library of functional programming primitives for Scala, contains a bunch of useful type classes. And it uses Simulacrum, first of all, which is very cool. But what we want to look at is where instances are defined in cats. First of all, for any data type, any type defined by cats itself, all of the instances are defined in the companion objects, because that's possible for cats to do, and that's the right place to put them. For data types that were defined in Scala, so for example, if you want to attach more type classes to either, and we don't have control, we want to improve on what we can do for either. We are not able to define those instances in the type class or in the objects because we have not defined them directly. And so what cats ends up doing is grouping all of the orphan instances, the ones that are not defined in either, in a certain package called cats instances. And this, again, helps with looking for them. And again, we have support for selective import via traits. So from Rust and cats, prefer companion objects for type classes and data types that you control. But if you can't, because you don't control neither the type class nor the data type, then group all orphan instances in a package, allowing selective import. And whenever possible, avoid overlapping instances, unless there's a specific usability need. So let's move on to something more, which is, okay, we've said that we should avoid overlapping instances, for example. But what do we do if we have multiple conflicting ways to compute an area, for example, as we had before? So we had spherical area and planar area. What we can do is just retain one as the default area. And if we wanted to then be explicit about saying this is the implementation of area in a different context, on a spherical context, then we can wrap the value that we want to calculate the area on and provide an implementation for that. So now, when we call this piece of code, this is only going to work if we have an instance for a spherical rectangle in scope. And there's no confusion anymore. So for this, for maintainability and readability, use new type for any conflicting instances, if it makes sense. In some other cases, it's fine to have multiple conflicting instances if you can be sure that your library user is going to be aware of the context the instances are going to be used in. So to wrap up, 3 main guiding principles that I think CATS and Simulacrum suggest and that other languages include directly for good usability of Scala type classes in a way that's non-confusing are discoverability, so let the user find your type class instances easily, readability, so make sure that it's clear which instance is being used at any point in the code, and coherence and maintainability, so make sure there are not overlapping instances if there's no need for them to exist, and make sure that a piece of code doesn't change meaning when you move it around the code base. And with that, I think I'm right on time, and I'm done. Thank you very much.